All right, let's finish this water unit talking about the oceans and a little bit about shorelines, but mostly about the oceans. Because, of course, if we're going to talk about water, we need to talk about water, and that's where most of the water on our planet resides. So the ocean basins, they cover over 70% of the land surface. And when you add up all the water in the oceans, it's over 1.3 billion cubic kilometers of water. And these oceans have been with us for quite a long time. Some of the earliest evidence that we have that there is water in the ocean basins, or I guess water on Earth in the form of oceans, goes back as probably about as far as 4 billion years ago. So our planet has been a water planet for quite a long time. And most of that water came from the interior of the planet. As the hot rocks inside the planet degassed, all that water vapor would come out. Think about a volcano steaming away. And that would add water to our atmosphere, which then would condense to rain and fall in and start filling our ocean basins. So that water from the interior is the main source of water on the surface of the Earth. And it ended up being salty. The ocean water is salty because you have a combination of both degassing at our mid-ocean ridges. So we have all this material. We looked at some pictures and videos of black smokers. They're releasing all sorts of elements into the ocean, including chlorine. And then the weathering of our continents dumps more elements into the oceans, things like sodium. Then the sodium and chlorine bond and form salts. So it's the combination of the fact that we have continents that weather and an active mid-ocean ridge system that gives us our salty oceans. And the oceans are where they are because remember that oceanic crust is thinner and denser than continental crust. So it sits lower and creates the basins that fill to become our oceans. Now, I think most people, when they think about the oceans, they think about waves. And waves are some of the most important features of our oceans. And the waves are actually just the product of friction, right? You have wind moving over the surface of the water, and there's friction between the water and the wind, and that produces waves that are moving in the water particles kind of move in a circle. And you produce these circular flow of water that are separated by some wavelength. So usually that's measured from crest to crest of waves. And the circular motion goes down into the water column, not to the bottom in most cases, but to about half the length of the wavelength. So if a wave has a 6-foot wavelength, then the circular motion that's producing the waves goes down about 3 feet. And that's what we call the wave base. But once the wave base starts to interact with the bottom of the ocean, like when it gets near the shore, it slows down the bottom of the wave because of all the friction between the water and the bottom of the ocean. And at some point, the top part overtakes the bottom part, and the waves will break. So when you're at the beach and watching waves breaking, that's because you've reached the point where the top part of our wave has overtaken the bottom part because the bottom part is slowed down by that friction from the bottom of the ocean. Now, waves can be generated by energy. We can also think about, or waves can be generated by energy. Waves can be generated by wind, but another way that we get the water in the oceans to move around is tides. So tides are just how the water on the surface of the earth is deformed by the gravitational attraction of the moon and the sun. The sun is a lot bigger, has a lot more gravity, but the moon is closer. So it actually brings more, the moon has a larger role in creating tides. And the tides will happen twice a day. They're diurnal. On a tidal day, which is slightly longer than the 24-hour sort of clock day, which is why the time of the high tides and low tide changes day to day. And the tides, the solar and the lunar tides, can either reinforce each other when they're in a line, call that a spring tide, or they can contradict each other. So when they're at right angles to each other, like in the bottom this figure on the left, we get what we call neap tides, when the sun and the moon are at 90 degrees from each other. And how high the tides are is the magnitude of these tides is a product of the coastline and the bathymetry. So most tides might be a few meters difference from high tide to low tide, but then there are places like the Bay of Fundy in Canada where the tides are 12 to 18 meters. That's like 40 to 60 feet of change of the water level, thanks to the sort of daily tides. The depths of the ocean, speaking of the bottom of the ocean, the depth of the ocean is highly variable. So more so than our land surface, where the deepest trenches go down 11,000 meters, so 11 kilometers to get to the bottom of the Marianas Trench. And there are lots of places that are really flat. We'll talk about the abyssal plains. And then there are places that are smaller shelves near the land surface. And most of the oceans are much deeper than the vertical side of the vertical portion of land above the sea level. So, and the trenches, the one thing I like about this cartoon looking at the depths of the ocean is that we tend to think about trenches as being these narrow canyon-like things. You can see that this XKCD cartoon shows the Marianas Trench with an accurate horizontal scale. And you can see that it's a lot more gradual than what we tend to think about. So the planet's big. The continents where they meet oceans, there are two different kinds of margins. Looks like the maps here somehow got a lot more pixelated than I'd like. But the eastern seaboard of North America is a passive continental margin where there's no active tectonic events going on. It's just the coastline heading down into the ocean until you reach the mid-ocean ridge. Active continental margins are where there are active tectonics. So you look at Japan, and it's got the subduction of the Pacific plate. So it's an active continental margin, and they have different shapes to them. So we'll first talk about passive margins and then talk about active margins. So in passive margins, we have this transition from the coastline to what we call the continental shelf, to the continental slope, then to a continental rise, and finally the deep, the abyssal plain. And the continental shelf, you can see in the image on the right that the slopes of these portions of the continents are really what define their names, right? Is that the continental shelf has a very shallow slope. It's a shelf. It's pretty flat. While the continental slope is pretty steep, that takes us down into the depths of the ocean that are 4 or 5 kilometers beneath sea level. So here's some pictures of topography and bathymetry near Los Angeles that show the shelf and the slope. The shelf here is only a few kilometers wide. Sometimes the continental shelf can be 500 kilometers wide in some parts of the world. It tends to have water depth that's only a few hundred meters, and it's pretty flat and can be carved up to some degree by canyons. So you can see one here just below where it says Santa Monica. There's some canyons that have been carved in, and we'll talk about those in a second. The continental slope is the steeper portion where you're going from the shelf to the abyssal plains, and the canyons cut into that. And it's usually during low sea level times or by landslides. And I apologize, those labels there, the shelf should be up on top of the shelf, not on the slope, and the slope should be on the slope. So those got shifted around a little bit at some point. So one of the ways that you create these canyons are what we call turbidity currents. They're sediment-filled flows. Think of them as underwater landslides that are triggered usually by earthquakes or maybe by just slope instability, and they can carry a lot of sediment down from the continental shelf and slope down into the abyssal plain. And on the left, there's a famous continental turbidity current that snapped a bunch of undersea cables over the course of a few hours. So these flows are moving down slope, but they can carry sediment out into the ocean for hundreds of kilometers. And they move kind of like a pyroclastic flow on a volcano, where you have these plumes of sediment-rich water moving through the rest of the water. So the diagram in the middle there shows how they kind of look like a cloud of sediment moving along, carrying sand and gravel, and usually not things that are really huge, at least not very far, but they help bring a lot of sediment out into the oceans. And the sediment can be carried out in these deep submarine canyons. So this is Monterey Canyon off the coast of Monterey in California. And it was partially carved when the sea level was lower, and we had a river flowing over the area when it was above sea level. And then part of it is carved by these turbidity currents. So you can see here that the Monterey Canyon goes out 100 kilometers and more out into the Pacific Ocean from the shoreline. And you can see it matches up with some of the rivers that meet the sea around Monterey. Once we get down to the abyssal plain, we're looking at the very bottom of the ocean. It's the flat, very far from the continental margins. It is the flat-lying sediment. It's mostly flat-lying oceanic sediment that is at the depth of 5 kilometers beneath the surface of the ocean. And the sediment that collects there is really fine muds. And those muds can be the sediment in the oceans can kind of be two flavors. One of them is called terrigenous sediment. That's sediment derived from eroding the continents. And then the other is called pelagic sediment. Pelagic sediment is material that settles through the ocean column. It might be some of the mud that's suspended in the ocean. It might be dead animals or animal detritus. It might be skeletons. And it accumulates at the bottom of the ocean at rates of only a millimeter per century. So this is this long-term settling of fine materials in the ocean that can fill the abyssal plain with either terrigenous sediments that are usually carried down by turbidity currents, or pelagic sediments that kind of drift down and settle out from the ocean water column. All right, so that's kind of thinking about passive margins. On the active margins, so on the left side of this or the right side of this diagram, they're different. They might have continental shelves, but they don't tend to be as large. They have continental slopes, but then they have a trench. So what you want to picture here is that the trench is formed from the point where the subducting oceanic plate heads underneath the continent. So these trenches, the sediment that is being shed off the continent and usually ends up filling the trench rather than making it further out into the ocean. So these trenches can be really deep too. They're 8 to 11 kilometers deep, depending on the geometry of the subduction zone. So those trenches are really the hallmark of active continental margins. You still have a continental shelf, you still have a continental slope. There's no continental rise because you have a trench instead. But you have this deep trench that's formed from that subduction. The other feature we have across the ocean are all these seamounts. Seamounts are just sort of random mountains at the bottom of the ocean. Most of them are volcanic, although a few are made structurally. So the map on the left just shows all of the seamounts that you can find across the southern Pacific. And most of these seamounts rise thousands of meters off the seafloor. Some of them can actually make it and be exposed on the surface. That's what you see on the right-hand side here. That they'll at first be a volcanic island, and then as the volcano wanes, it will erode and become an atoll. So an atoll are these islands that are usually small with lagoons and a fringing reef around the edges. So islands that are the older islands of the Hawaiian island chain are these atolls, while the main islands of Hawaii are still in the sort of a volcanic seamount stage instead. So that was a very quick overview about our oceans. And we'll talk about them some more when we talk about climate, because they play a really important role in the Earth's climate. So we'll come back to them in the next unit.